Hello students. In this video we're going to expand on this concept of gas mixtures that we covered in our last video to talk about a concept called the mole fraction. So I'm going to go ahead and write that down, mole fraction of a gas. A mole fraction of a gas is the fraction of the total moles of a gas in a mixture that is constituted by that gas. Now, just to clarify what that means, if you take the total moles of all of the gas particles in the mixture, and then you figure out what fraction of them is, for example, oxygen gas, then that is the mole fraction of the oxygen. If we go back up here to our example where we were talking about a mixture of nitrogen and oxygen, you can think of them as marbles in a bottle. And we could talk about the fraction of the red marbles, which would just be the number of red marbles divided by the total marbles. And so that would be the red marble fraction. Well, the same way we can do a mole fraction for a particular gas. Okay? And that's what we're going to do. Now, a mole fraction is technically represented by a capital Greek chi. So it's kind of like a swoopy capital X. That chi, we would spell it out in English as chi, but that is the symbol for it. That represents the mole fraction, and it is calculated according to a simple equation. And that equation is, I have not given myself much space here. I'm going to come down here and I'll just write the equation down here so we can see it. The equation, the mole fraction for some gas A equals the number of moles of gas A divided by the total number of moles in the sample. Okay? I think you can see that if we happen to multiply that by 100, we would end up getting a percent. Right? We would get a percent of all of the moles of gas in the mixture that are that gas A. But before you multiply it by 100, you have a fraction. So there's the general equation to calculate a mole fraction. It is, in fact, the same equation that you would use to calculate a fraction for anything. The number of red marbles in a jar divided by the total marbles in a jar would give you the fraction that are red marbles. So there's a sample problem A, and I think this will be fairly straightforward for us. It says, what is the mole fraction of O2 gas in the vessel that we described in this problem above? Well, let's go back up here. And I'll remind you that the total pressure this was the sample problem. And I was told that I have 1.5 moles of nitrogen and 2.0 moles of oxygen. So those are the individual molar amounts. And with those two individual molar amounts, I would like for you now to calculate the mole fraction of just the oxygen down here. So please do that for the mole fraction of oxygen. Take a moment, finish that, get your answer, and come back when you're done and I'll review that. Okay, coming back to this work, we're going to input the number of moles of gas A, which is the oxygen in this case. So we're going to say the mole fraction of O2 in this case, right? That's what we're calculating. And the total, the moles of oxygen gas we were given as 2.0 moles of oxygen gas. And we're going to divide it by the total number of moles in the sample. And hopefully you caught this. To get that number for the denominator, we're going to have to add these so that we get the total number of moles. So 1.5 and 2.0 is 3.5, right? 3.5 total moles. And we don't want to leave the fraction like that. We want to resolve it. And to 2 sig figs, that gives me a value of 0.57. And this is a unitless number because moles and moles will cancel. So there's my answer to 2 sig figs, okay? So what is the mole fraction of oxygen gas in a container that has 1.5 moles of nitrogen gas and 2.0 moles of oxygen gas in it? Well, the mole fraction of oxygen gas is 0.57. And again, if we chose to, we're not expected to here, but if we chose to, we could multiply that by 100 and get the percent. And so you would see that 57% of the moles of gas in that vessel are oxygen molecules. All right, moving on. We're going to move forward now and combine these two aspects of the gas mixtures. The Dalton's law of partial pressures that relates the total pressure of a vessel to the partial pressure of each gas. And we're going to combine it with the mole fraction relationship. And that is going to give us a relationship between the partial pressure of an individual gas in a mixture and its mole fraction. So here it is. Here's the equation. The partial pressure of a particular gas, A, is equal to the total pressure on all gases in that sample times the fraction that is that gas. That would be the mole fraction of that particular gas. So all this equation is saying is, if you take the total pressure of all the gases in a vessel, and then you multiply it by the fraction of moles that is a particular gas, then you'll get the partial pressure of that particular gas. So I've got a sample problem down here for you. We're going to put this into use. We have a vessel at a particular pressure, 2.44 atmospheres. That is the total pressure on the whole vessel. So right away we're seeing P total is being given to us. And it contains that many moles of NH3 gas, ammonia gas, and that many moles of H2 gas. So we're asked to determine the partial pressures of each gas. So you'll have two different calculations to perform. First calculation will be to determine the partial pressure of the ammonia gas, and then the second calculation will be to determine the partial pressure of the H2 gas. And you can use this equation. And remember, in order to be able to get the mole fraction, you may have to go to the previous page, and use that equation to be able to get a mole fraction, right? So that then you can plug it into this equation to solve for the partial pressure for each of these individual gases. Go ahead and give that a shot. Determine the partial pressure of each of these gases. When you're done, resume the video, and I will work through this. Okay, so I have two calculations I'm going to perform because I'm going to determine the partial pressures of each gas. So I've got a calculation for the partial pressure of the NH3, and I'm also going to determine the partial pressure of the H2. And I know that according to this relationship up here, the partial pressure of the ammonia is equal to the total pressure of all of the gas mixture times the mole fraction of just the ammonia, right? So I'm going to start plugging in values. I know that the total pressure on the vessel is 2.44 atmospheres. And the mole fraction of the ammonia is the number of moles of ammonia, which is 0.21, divided by the total moles of all gas in the mixture. So that's 0.21 plus 0.15s. Total, right? So if I get my calculator, I can do that math. And rounding to 2 sig figs, because of these values here, I get a partial pressure for the ammonia gas, which is 1.4 atmospheres. And before I move on, I see if I can make sense of that. So the total pressure was 2.44. If this is a partial pressure, it must be below that number, right? Because this is going to contribute to that total. And it must be proportionate to the fraction of the moles. And we can see that of the NH3, there's 0.21 moles. there's 0.21 moles in the mixture compared to 0.15 moles of the H2. So a little over half of the moles are due to the ammonia. Well, this pressure is a little over half of the total pressure, so that seems reasonable. Now, to determine the partial pressure of the H2 gas, I could do this the exact same way. Or I could just take the total pressure, subtract the partial pressure of the NH3, and whatever's left must be the partial pressure of the H2. So either of those methods would work. I just want you to recognize that they both mean the same thing, right? Let's go ahead and just plug them in here. The P total times the mole fraction of the H2 gas is going to give us our partial pressure of the H2. So the total pressure is 2.44 atmospheres again. And now we're going to have the mole fraction of the H2 gas. So it's a 0.15 moles of H2 divided by the total moles, which is the same as up here, 0.21 plus 0.15, which that equals 0.36, right? Moles total, 0.36 moles total. And now I do that calculation. And I can see right away that my answer should be somewhere around 2.4 minus 1.4. The answer should be about 1.0, right? So let's do the math and calculate and see if I get that answer. And there we go. My calculator says that it's 1.016666 and so forth. I rounded 2 sig figs, and it's 1.0 atmospheres. And there you go. That's true. Notice that I cannot be as precise out to that second place past the decimal in my total here because of these values that I used to generate my partial pressures. And there we go. That's how we calculate a partial pressure of a gas. Now, why is this useful? Well, you may not know the temperature of a sample of gas. And without the temperature of a sample of gas, you can't use the PV equals nRT equation to calculate a pressure, can you? But by using the mole fraction and Dalton's law of partial pressures, we don't need the temperature of this gas to be able to determine their pressures if we are given the total pressure and we are given some way to calculate the mole fraction, either being told the number of moles outright or being given the number of grams, for example. If you're given the number of grams of ammonia gas, you'd have to do a little side calculation to go grams to moles first. And then you could plug in the mole values and figure out the mole fractions. All right, there we go. That is how we use Dalton's law of partial pressures with mole fractions to be able to calculate the partial pressures of individual gases in a mixture when you don't have the temperatures of the gas.